In the second lecture, I'm going to tell you what is the convex body isoperimetric conjecture. So now let's go back to Dido's problem. Suppose the princess now arrives at an island instead of a continent. Then we are faced with the following isoperimetric problem. Okay. Here is the island. Now we have a bounded domain in the plane, and we are asking how you can circle a piece of land with minimum length. Okay, so naturally we define this function I sub omega of a. So given an area greater than 0 and less than the area of omega, we look for this isoperimetric problem. Okay. So gamma should enclose a fixed area of A, but with a minimum length. And this function I sub omega is called the isoperimetric profile of omega. Okay? So it's defined on the open interval 0 to area omega. And here is a picture. So this is a picture of Taiwan. And we know that you don't have to waste any material along the coastline. Okay? You just have to take care of the interior. And now we can state the convex body isoperimetric conjecture in the plane. Let omega be a convex domain with area pi that is the same as the area of a unit disk. Then the isoperimetric profile is bounded from above by that of the unit disk for any a between 0 and pi. And of course, this is the planar case. One can also ask the higher dimensional analog, but let's focus on the planar case in my lecture. A little history. This conjecture is proposed by Professor Wickremala in 2002. And the name of the conjecture is due to Professor Frank Morgan. Oh, here's the announcement of the original seminar talk of Professor Wickremala. Okay. So there are only a few of known results, and actually two, and we can give of them here. The first is due to a group of mathematicians. They show that for half of the area, the conjecture is true. Okay, given any omega, so they prove it for convex omega. The isoperimetric profile is bounded by that of unit disk, and they also characterize the equality case. It can only happen if and only if omega is the unit disk. And the proof uses the convexity in an essential way. Okay. Oh, I should remark that in the original conjecture, no convexity is assumed. Okay, I should point it out here. Okay, but to my knowledge, no counterexample is known even with convexity or not. So. And in my talk, I will focus on the convex case. Okay, and in this theorem, the omega has to be convex. Okay. The second known result is due to a group of undergraduates. Okay, this is obtained in an REU program supervised by Professor Frank Morgan. They show that the conjecture holds for regular polygons. Note that regular polygons must be convex. Okay? And the idea of Berry's result is as follows. Suppose now we have a square that has the same area as a unit disk. So we know that the area of this part is equal to this part. Okay, and suppose the gray arc is minimizer for the isoperimetric problem for a disk, we can rotate the disk so that it passes through the intersection of square and the circle. And on the other hand, I draw this blue arc for comparison. We can see that this blue arc encloses more area in square. So there is a common one. There is a common one here, and the blue arc encloses this part of the area, while the gray encloses this part of the area. So the blue arc encloses more area in square, and it is shorter than the gray arc. Okay. So the isoperimetric profile for the square is less than that of the disk. Of course, this is the trivial case. In reality, you have to do a case-by-case study. For example, the arrangement of the minimizer for disk may be like this. May enclose more area, and then you have to do a detailed analysis. Okay. And now let me present our results. First, we recall some standard notion. A vertex of a curve is a point at which the derivative of curvature is 0. And recall the famous four-vertex theorem says that a closed plane curve has at least 4 vertices. Our first result is, suppose omega is a convex domain satisfying the first is the assumption of the conjecture. The area is equal to pi, and we assume that omega is symmetric with respect to x-axis and y-axis, and the boundary has exactly 4 vertices, the minimum amount of vertices. Then the conjecture holds for omega. For example, you can say the conjecture holds for, say, ellipses. And our second result is a perturbative one. We show that the conjecture holds for perturbations of unit disk. More precisely, suppose we have a family of domain coming out of the unit disk, and all of them have area pi. Then, for any a, we show that the first derivative of the isoperimetric profile is negative. Or if the first derivative doesn't bring the isoperimetric profile down, the second derivative does. So this shows that the conjecture holds for perturbations of unit disk. I'll sketch the proof of these two theorems in my third lecture. But to end this lecture, let me give you some background materials. The first is the Ionin-Pestov theorem. So, given a domain in the plane, the curvature of its boundary satisfies this. So the maximum of curvature is bounded below by the square root of pi over the area of omega. And the equality holds if and only if omega is a disk. So we will only use a trivial consequence of this theorem. Suppose omega encloses area pi and is not a unit disk, then the maximum curvature of its boundary is greater than 1. And moreover, we can use the isoperimetric inequality to show that kappa minimum is less than 1. This is more elementary. Let me present here. It is independent of Ionin-Pestov inequality. So suppose we have 2 pi, we always have 2 pi equals the integral of curvature along the boundary. And it is, of course, greater than or equal to kappa minimum times the length of the boundary curve. And using isoperimetric inequality, we get it is greater than 4 pi times a. Now, A is assumed to be pi. This is kappa minimum of 2 pi. Okay, so we show that the minimum curvature is less than or equal to 1. And since omega is not a unit disk, the equality case cannot be achieved. Secondly, we need two consequences from the first variation formula of length. So the first one says that the critical points of the variational problem must be circular arcs intersecting omega orthogonally. Okay, this should be well known. We have an analog in the higher dimensional case. The critical points of variational problem are a free boundary constant mean curvature hypersurfaces. And in my talk, we will call a circular arcs intersecting the boundary orthogonally perfect arcs. And the second lemma is, suppose we have a family of perfect arcs with enclosed area A. Okay, so we parameterize a family of perfect arcs with their area. And suppose the curvature is denoted by K, which is a function of A. Then the derivative of length with respect to A is equal to the curvature. Okay. So I will prepare a supplementary talk in which I give proof of the Ionin-Pestov inequality and the first variation formula of length. And from there, we can see immediately these two lemma hold. Okay. So this is my second lecture.